Hello, this is Michał, one of the organizers of QRST. Unfortunately, we have not recorded the first part of the presentation by Dr. Claire Edmunds. I'm really sorry for that. She talked about some introduction to quantum control and ion traps. I have added her slides into this video so that you can get a rough idea of what she was talking about. Sorry, there were some technical issues and we didn't get it. Dr. Claire Edmunds works at the University of Innsbruck in the Quantum Optics and Spectroscopy group led by Professor Rainer Blatt. Claire specializes in quantum simulation and quantum control using trapped calcium ions. In 2021, she was awarded a research fellowship with the Erwin Schrödinger Center for Quantum Science and Technology after completing her PhD in experimental quantum physics at the University of Sydney. Her work strives to improve the performance of quantum platforms in realistic laboratory conditions in the path to build reliable quantum computers and simulators. Once again, I'm sorry for the technical issues, but the core of her presentation is still there, so I hope you'll enjoy listening to that.
Then we need to do something to the errors before applying quantum error correction. And that's the idea of quantum control. So I'll start off by introducing one simplest concept from quantum control, which is a dynamically corrected gate, or a DCG. For those of you familiar with a spin echo, this is a really similar concept, but it's for a driven rotation rather than an idle period. In this talk, I'm going to talk about primitive gates a lot. This is just the easiest way of getting from point A to point B in the block sphere, following the geodesic, just round from the top to the bottom. It's a square pulse of microwaves or a laser. Whilst it's really easy to do, it's very sensitive to errors. If you have a frequency error in your control, then you're going to rotate around the wrong axis. If you have an amplitude error, then you're going to rotate too far or not far enough. On the other hand, you can run a DCG. This is a series of amplitude, phase, or frequency modulations. It's a longer pulse and takes a much more complex trajectory around the block sphere, but still runs from point A to point B as required. Additionally, the series of modulations ensures that any errors that might be happening are undone throughout the course of the gate. I should specify very specifically what errors we're talking about. We're talking about coherent unitary errors, slowly varying or even static, such as calibration type errors. These are the errors which a spin echo works really well to deal with. The first half of the gate will accumulate some sort of error, and then the second half of the gate will unwind it using the knowledge of what it was against itself. To see this in action, we can look at some experimental data. This is a single ion with 10 pi pulses. I'm engineering either a frequency error in the control or a pulse length error, so an over-rotation error. I'm then measuring how accurate the final state is for what I want it to be. In this case, 0 is a perfect state, it says no error, and 1 is the entirely wrong state. I've flipped to 1. When I repeat this with 4 different types of gate constructions, I've chosen primitive gates, corpse, which is a DCG to suppress detuning errors, BB1, which suppresses over-rotation and pulse length errors, and corpse in BB, C in BB, which suppresses both. Looking at the results, we can see that the black data for the primitive is very sensitive to the engineered errors, and quickly the quantum state diverges from what we want to have. The corpse and the BB1 perform really well in one quadrature and poorly in the other, whereas the C in BB is robust in both. So this is showing how we can use these DCGs to suppress errors in our quantum sequence, despite the fact that there is a physical noise source or a physical error source happening. A big question to ask, and the question you should ask, is, do we need quantum control? When should we use it? If we've got these DCGs, should we just always be applying the most complicated one, the most robust one to our algorithms? And the answer is subtle. So to understand this, I want to talk about the system I was using in Sydney. This was an terbium hyperfine ground state. It was a microwave frequency transition, which allowed us to use a really low noise microwave source. We got very low randomized benchmarking error rates, 10 to the minus 5, and pushing down to 10 to the minus 6. This is not a system where you'd want to apply quantum control. because you're already getting error rates which are perfectly suitable for your all purposes. And chances are, if you use quantum control, things are going to get worse. So when do we need it? And the answer comes with scaling up. As we scale up our system in terms of qubits and gates, we introduce a whole range of potential error sources, such as crosstalk. We increase the parameter space required for our calibrations, and we increase the overhead needed. All of these things are going to introduce potential errors, which are going to be very difficult to eliminate at the physical layer. In particular, in Sydney, we found that we had a gradient in our magnetic field and in our microwave field intensity, which meant that the Rabi frequencies and the qubit frequencies across the ion string were different. With the microwave field, it's a global field. It illuminates all ions simultaneously, so we can't calibrate it uniquely for each ion's requirements. To quantify how bad this is, we did randomized benchmarking. This is 10 different qubits, 10 ions, using a global microwave field to run simultaneous randomized benchmarking. What we see is that when we calibrate the field to the frequency, the amplitude, the pulse length, to the leftmost qubit, our calibration qubit, we achieve a randomized benchmarking error, which is really on par with a single ion in the trap. However, moving away from that ion, the error rates get worse due to the gradients, and we actually get over an order of magnitude worse by the time we're at the 10th qubit. This is problematic for two reasons. One is just that far right error rate is quite high. It's just not a good result. The other is that this inhomogeneity in the error rates really violates a lot of assumptions that we make when we talk about properties, processes like quantum error correction. In general, we want our qubits to be indistinguishable. We want them to have the same error rate. In this case, we're going to be limited by that top error rate, and that's what we're going to have to sort of take as our assumption for all of them. So we're left with a problem. There's two possible things we can do here. One is that we can not use microwave gates. We can use focused laser gates as well, which we can calibrate individually. The problem is that the laser gates are a factor of 10 to 100 times worse than the microwave gates because the sources are much noisier. So we'd really rather not do that. We'd like to use our microwave gates if we want to do global rotations. And that's where quantum control comes in. We're dealing with a static calibration error, which is the exact sort of error which this project is designed to target. And sure enough, we can repeat this experiment using BB1 gates designed to suppress the dominant over-rotation errors. When we measure our RB error rates, we find a 10 times reduction in the spread and a 3 times reduction in the average error rate. So this is fantastic. We've homogenized our error rates and we've reduced the average. This is exactly what we wanted to see. And it's really enabled us to use global microwave gates in our system.
And it has the associated things like the personnel requirements, the facility requirements.
Sorry, was that directed?
No. Sorry, that was like someone unmuted, I think.
No problem. But before I move on, I just wanted to point out something quite important, which is this leftmost qubit, the calibration qubit. You'll see that with the BB1 gates, the error rate got worse. And this is what I was alluding to with the single ion in the trap. Using quantum control in that circumstance wouldn't have helped us. We didn't really have any calibration errors in that qubit because we'd calibrated quite well. And the longer pulse length of the BB1 gate meant that we just introduced more decoherence and more sort of higher frequency errors into the system. And this is the trade-off you've often got to take with quantum control. And it's the reason why you need to really understand your system before you can use quantum control. And that's where we come to the second half of my talk on error characterization. To use quantum control, you want to tailor the appropriate solution for your system. And that you want to use it judiciously. And that means that you need to understand your errors. You need to understand how large they are. What sort of quadrature are they in? Are they over rotation? Are they off resonance? What sort of correlations do they have? Are they coherent or incoherent? And so that brings me to the topic I'm going to talk about now, which is an error characterization routine looking at temporal correlations in single qubit circuits. The reason why this is an interesting project is because these sorts of errors, highly correlated errors, are quite detrimental for quantum error correction. They build up really quickly and violate a lot of assumptions, increasing the overhead we're going to need. The other reason they're great, so it's interesting to consider, is because these sorts of errors tend to be good candidates for quantum control, because if they're correlated and coherent, we should be able to echo them away by using some sort of DCG. So for this project, we're going to consider a single qubit quantum circuit, like you can see on the screen. It's going to be built up with some series of gates. And in general, there's going to be some sort of noise happening. This can be in the lab, on the laser, it can be anything. The noise is going to create errors, and these errors will have some correlation length. That's going to tell you how related the error is at the first gate to the 100th gate in the sequence. To understand what these correlations are, we can't just probe in at every point in the sequence. Instead, we want to just use the final projective measurement to somehow extract that correlation length. It turns out this is possible. You have to use the statistical properties of those final projective measurements. So to start off with, I want to look at a noisy gate, a single noisy gate, which is affected by some error channel. If the error channel is unitary, which is what I'm going to assume from now on, then you can decompose the gate into an ideal gate and an error operator. The error operator is going to depend on what error channel you're considering. Is it over rotation or off resonance or something, some sort of hybrid problem? This entire protocol can be done for any unitary error channel, but without loss of generality, we can just assume we've got a particular one, let's say off resonance. So when we calculate the error operator for that, we're going to find some sort of error operator which encapsulates the strength and the quadrature of the error for that gate. Is it sigma x, y, or z? Given a particular sequence and a particular error channel, we can take these series of error operators and map them to Pauli space, to Pauli error space. This is what we like to call it. It's a space which encapsulates what sort of errors are happening to your system, sigma x, y's, or z's. Each sequence plus a particular error channel can be translated to a deterministic random walk. That's an intrinsic property of the sequence. Some of them are going to be long, some of them are going to be short. And I'll show later that that actually relates to how susceptible that sequence is to correlated errors. Oops, I'm running out of time, pardon me. So you get these random walks. And then for each noise realization, each actual realization of the error process, we're going to scale the steps of the random walk by the strength of the error that was present during that realization. If there's no noise, the walk shrinks to 0. If there's quite a lot of noise, the walk's going to be made quite a lot longer. We actually scale the steps by both the magnitude and the sign of the noise. So the steps can be flipped back on themselves. When we average the net scaled walk over many noise realizations, we'll get a measure of the infidelity, the expected infidelity of the sequence. This is how we identify uncorrelated versus correlated errors. If we have an uncorrelated noise process that changes every gate, then it's going to completely distort that characteristic random walk. It's going to flip it back, twist and turn it, and leave you at some random point in Pauli error space. And I've shown this here for 10 different circuits with 1,000 error realizations. It completely scatters the random walk final positions. If you have a correlated coherent error, which is static over the entire sequence, then all it can do is stretch or shrink the random walk. And you'll find that the final positions for a particular sequence will stay on the same line, just depending on how large the noise was in that realization. This is all calculation, but now I can show you some actual experimental data. So this is a single qubit with some randomized benchmarking style sequences made up of Clifford gates. We've applied these with some engineered noise, either correlated, static over a sequence, or uncorrelated, changing between gates. We've then sampled it over increasing noise realization, sampled from a Gaussian distribution. When we look at the fidelity, so this is a distribution of infidelity here, the sequences under uncorrelated noise rapidly converge towards some sort of mean value. And this is a representation of the true average error rate of your noise process. The correlated distribution, on the other hand, remains really broad. We get this broad distribution that doesn't really change on the noise averaging. That's because the structure of the circuit and of the random walk does not get changed by our error process. It can only preserve it. It only stretches and shrinks it. So if we think back to that first picture of those intrinsic random walks, some are long, some are short, the long ones are error amplifying. They're going to build up correlated errors. And they're these ones over here in the tail. The short ones are error suppressing. They've actually got inbuilt quantum control. And as we average over the noise process, they're going to remain pretty high fidelity no matter what happens. A nice way to think about this is like a Rabi versus a Ramsey experiment. Rabis are really good at amplifying amplitude errors, and Ramseys are really good at amplifying off-resonance errors. So if you look at their random walks that you would calculate for the two different error processes, Rabis have a long over-rotation random walk and a short off-resonance, and Ramsey's the opposite. We can plot the distribution variance, the variance of these distributions as we increase the noise averaging. For primitive gates, we rapidly saturate because we're dominated by that circuit structure that can't get averaged away. With the uncorrelated errors, we get a 1 on n type scaling like the central limit theorem, as all those results converge to a true mean. Given this metric, I just want to finish off by showing how we can use quantum control to suppress correlated errors. So I said before, these correlated errors are particularly detrimental because they build up so quickly. So we absolutely want to target them for quantum control to get rid of them and precondition our system for quantum error correction. Here, I've got some experimental data. I've taken the same sequences and now applied a combination of correlated and uncorrelated noise simultaneously. When you use primitive gates, you find that the distribution remains broad. The variance rapidly saturates because we're dominated by the correlated noise component and the circuit structure. With the same noise and the same sequences, if we replace the gates with DCGs, either WAMP or QUARPS in this case, we recover the 1 on n type scaling as if there was only uncorrelated noise present. And sure enough, we measure a 50 times reduction in the correlated noise component. We also see an 8 times increase in the uncorrelated noise component. And this is this trade-off you need to play again. You are going to expose yourself to more decoherence and high frequency noise with the longer gates. But in general, that's often worth it because those sorts of errors are more targetable with quantum error correction. So with that, I'll wrap up. I hope I've given you a little taste about why I find quantum control so interesting and what it can do, and also when and where it should be applied. It's a really powerful toolkit. It can be used to reduce the frequency and precision of calibrations in large systems, can reduce and homogenize error rates, and reduce temporal correlations between gates and spatial correlations between qubits. I haven't had a chance to talk about all of our research, but there's some different references down there at the bottom about some of the things that I did during my PhD. If anyone has any questions, feel free to ask. But broadly speaking, this whole talk has fit into that virtual layer of the quantum architecture. And now you're going to hear about layer 3, quantum error correction, what you get to do after you've got your errors dealt with. Thanks so much.
Thank you very much. Do we have any questions?
I have a few questions.
Yeah, please.
Yeah, thanks for the talk. I'm curious, when you collect the data, when you were collecting the data for the random walks, how do you collect that data? Do you have to truncate the circuit at multiple, each step that you wanted to collect? Or I know part of the graphs like some of these were simulated, right?
Yeah. So this is just a calculation. We actually have an analytic calculation that you can calculate what these random walks are for each sequence. And that's going to tell you, is this sequence going to be really susceptible to correlated errors or not susceptible? And then the data is taken by running an entire sequence and just measuring at the end. That was the whole sort of, motivation of this project. We didn't want to probe. We didn't want to break up the circuit and measure in between. We just wanted to use the statistical properties of averaging.
Okay. So then that probably means you had to have a good noise model that characterized, your actual hardware, right? In order to analytically determine the random noise walks.
That's absolutely true. The engineered noise we used was probably a factor of 10 larger than our intrinsic noise, off the top of my head. So we didn't have to worry too much about the intrinsic noise because we knew that what we were engineering would be predominant, particularly when it came to verifying this technique. We did do some work looking at intrinsic noise, both on the single qubit and on a multi-qubit system. The multi-qubit system was quite interesting because we had the gradient. So we saw that we got quite a large intrinsic correlated error because of that microwave field gradient.
Great, thank you.
Pleasure.
We have time for one more question.
I have a short question. I'm curious about, thanks for the talk, by the way, very nice talk. What is the cost of maintaining these trap ions quantum computers? I mean, do you need to calibrate them every, I don't know, twice per day or something like that, as happens with superconducting circuits quantum computers?
Yeah, so we do calibrations throughout the day. There's a lot of things we need to calibrate. So we need to calibrate the frequency and amplitude of our control field. Some calibrations we do every 3 minutes to give you an idea of how regular they are. Other ones we do once an hour. It depends how much we expect a particular thing to drift, like a laser or a magnetic field. It also depends on how sensitive we are to that drift. If you've got quite a bit of wiggle room before you see bad results, then you're not going to calibrate too often. But yeah, no, there's a lot of calibrations we need to do, and particularly as we get more ions, it really increases. So that was always a nice thing about using these DCGs. You can calibrate less frequently because they improve how robust you are to this sort of drift.
Okay, thank you.
Pleasure.